Today we're going to be talking about something a little bit different, but at least a little bit building off of the sorts of discussion of various risks that we've been talking about previously. Today I want to talk about this sort of question: how do we actually become confident in the safety of some system? So, previously we've talked a bunch about what sort of problems might arise when you're training various different systems. And today I want to move into this question of evaluation, right? We have some understanding of when to say no, right? When to believe that there might be a problem with some system. What sort of analysis might lead us to believe that some particular training regime is going to lead to an algorithm that is dangerous in some way. But what we don't yet have is some understanding of how to say yes. Some understanding of what makes a particular proposal, a particular approach to trying to build some sort of advanced aligned AI system, one that we should trust, one that is good, one that we can believe in, right? What are the sort of factors that might lead us to actually have confidence that a system is going to do the right thing? That's sort of the thing that we want to address today. OK, so we got to start with this sort of basic question that we've been talking about a bunch throughout the series, which is, when we train an AI system, when we use machine learning to actually produce some algorithm which has some particular property, what do we actually know about that algorithm, right? And fundamentally, and we sort of stressed this a bunch, all we really know is we know that it is some algorithm that performs well on the data that we gave it. And it's some algorithm that was selected by the inductive biases of the training process to be structurally simple, to be the sort of algorithm that has a large basin, all of these sorts of basic properties. We talked last time about all of the various different ways in which the inductive biases could go, and all of the sort of uncertainty that we can have surrounding this. But the basic thing that we always know, is just, well, it's some algorithm, it performs well on the training data, and it was selected by the inductive biases. OK. And so the basic problem that we have is that if we want to be confident in the safety of a system, we need to not just know its training behavior, we need to know its generalization behavior. We need to know what will happen when you take that model and you deploy it in some new environment, when you give it some new task, what actually happens? What sort of behavior does it have? What sort of basic structural algorithm do we actually learn? And so we need to know more than just this basic fact about what it does on the training data. OK. Yeah, question.
So you mentioned before about adversarial training and holding out certain data points. Is it the case that if you have something that performs well on training, and then it performs well on some held out data, are we then confident it will perform well on all held out data, or is it really more of a domain-specific problem about a distribution?
Yes, that's a really good question. So I think that the answer is, well, something, right? If you have some case where you're like, well, we don't know whether it's going to have good generalization behavior in this new individual test case, and then we test it there and it has good behavior, you have learned something about the basic structure, the basic thing that you in fact did when you produced that algorithm, right? You produced an algorithm which actually had a particular generalization property. If I train on, going back to original example from the first talk, if we train on something like classifying the Pac-Man from the the little triangle with a block, they're different colors versus shapes. If I then try the generalization task and I learn that, well, I always learn to classify based on color, I have in fact learned some useful fact about my inductive biases and about what algorithm that I learned. But the point, the sort of concerning thing is that there's going to be a lot of situations where we sort of don't expect to always be able to tell, the sorts of facts that we really need to know about our model in terms of its, safety just by that sort of process alone. So we talked about this a bunch in the last two talks about deceptive alignment, where with deception specifically, it's a case where it's very, very difficult to actually gain any confidence in whether your system is or is not deceptive if the only thing that you know is these sorts of properties where, well, I did a bunch of adversarial training. Because as we talked about previously, there are multiple different model classes which are compatible with the sort of limit of adversarial training, some of which are aligned and some of which are not aligned. And so we need to know some additional facts other than just that. Now, that being said, and we'll talk about this a little bit later on today, but there are some ways that you could sort of use this extrapolation to gain sort of more evidence even about deceptive alignment. So, for example, we might believe that, well, because we have seen many times, if we train in this particular way, we're very likely to get a model that has these properties, and those properties are such that they preclude deception. So for example, if we train in this way, we always get a model that is not doing long-term reasoning or something. Then we're like, OK, if we can believe that that trend will continue to hold, then you can believe that particular training procedure is unlikely to lead to deception, even if you don't directly have evidence that the model itself is or is not deceptive. You have some evidence from sort of extrapolating. But then the question, of course, becomes how much evidence is that? So we'll talk about these sorts of various ways to gain evidence. I think the place that I want to start right now is just with this question of, what do we need, right? What sort of structure should we be looking at if we want to understand, why a particular training procedure is safe, why it's sort of, we might believe it's going to yield a sort of algorithm that we trust. So the basic thing that I'm going to say we sort of, want is we want, first some theory of what mechanistically the model is doing. So if you have some particular training procedure and you want to argue this training procedure is safe, the first thing that we need to know is, well, what sort of algorithm is it actually trying to produce, right? What is the structurally simple algorithm, the basic thing that we actually want it to be doing at the end of the day? Why do we need to know this? Well, I think it's really important for a couple of reasons. So to start with, if we don't know this, it's really hard to have an understanding of arguing whether it is going to be safe or not, because the space of possible algorithms is really, really big. And if we don't know what sort of target within that space we're trying to hit and what sort of target we believe we might have evidence we're going to hit, and we're just sort of making very general arguments about, is this sort of in general like to be pushed in a safe or unsafe direction, I think it's very hard to sort of be specific about, okay, what are the actual alignment properties of the system? Do we actually believe it's going to do the right thing? And so I think I really want to push towards what we're going to be focusing on is these very specific stories where, we have some specific story for this training process produces a system that, in fact, is implementing this sort of algorithm. And then we want to ask, do we actually believe that? Is that algorithm actually safe? And of course, that's the second thing that we need. Given that you have some particular model for what you think, what sort of algorithm you think you're going to learn, you also need some reason to believe that you're actually going to get that algorithm. Some reason to believe that the sort of algorithm you want the model to be implementing is in fact the algorithm you're actually going to get when you run your machine learning process. So these are the two sort of most basic components that I think we need when we're sort of trying to understand, a story for why a system is safe. So we're going to give these things names. We're going to say that the first one is a training goal. This is sort of the goal of our training process. We want to produce a system that is well described in this way. And then the second thing is sort of our training rationale. It's like why we believe that our particular training process is actually going to produce a thing that falls into that class, that actually sort of satisfies that goal. So what is the goal sort of mechanistically, structurally? What sort of algorithm do we want to get? And then why do we believe that our training process will produce that algorithm? OK. So together, we're sort of going to call these two things a training story. So we're going to say, a sort of a combination of a goal, this is what we think our machine learning process is going to produce, and a rationale, this is why we think it's going to do that, is a story for why you think your thing is safe, right? If you come to me, with some particular machine learning system, and you want to say, I think this machine learning system is safe, well, then you need to say, we're going to say, you need to say, what is it? What sort of algorithm do you think it's going to learn? And then, why is it actually going to learn an algorithm, right? OK. So let's sort of just give a very simple example. Yeah, question.
I might be over-reading into the notation on the previous slide, but the previous notation was like training goal plus training rationale implies training story instead of equals training story. Is that a specific difference that's worth pointing out?
No, that's just an arrow. I'm just like, if you have both of those two things, you have a training story. This is just like the components of a training story. Yeah, I don't mean to give a sort of implies relationship there. OK, so let's do a really simple example. So here's something that is, in fact, probably safe. I want to train a thing to classify cats and dogs. And even then, we still sort of want to work through what is the training story, right? So we're going to say, well, what is the training goal? Well, in this case, we want a model that does cat-dog classification. But it's worth pointing out that there are some models that would, in fact, do a good job on cat-dog classification, some algorithms that one could be implementing that would do a good job on this task that we don't want. So an example of an algorithm that we don't want that would do a good job on cat-dog classification is agent trying to maximize paper clips, right? As we talked about previously, if you have some agent and it has some long-term goal about the world, then it is in fact going to do a good job in whatever training environment you put it in because it wants to pretend to be doing a good job so that it can eventually do whatever thing it wants in the world. We obviously don't want that. And so we're gonna say, OK, the thing that we want is not just like anything which does a good job on cat-dog classification. When we're training a cat-dog classifier, we really specifically want a thing which is implementing simple human-like heuristics for cat-dog classification. We don't want it to be doing some crazy sort of deceptive thing. We just want it to be doing the basic thing of, okay, humans in fact use some basic visual heuristics to understand whether a particular thing is a cat or a dog. We just want to capture those heuristics and implement them in our model. If we believe that it's in fact doing that, then we think it's going to be safe. And then why do we think it's going to be doing that? Well, we have some belief that when we train a convolutional neural network on a task that's relatively simple, that the simplest sorts of heuristics are going to be these same sorts of human image heuristics. When we look at an image, we sort of have some idea of how to distinguish between a cat and a dog. There are basic structural facts and about that image that let us do this distinguishing. And we have some belief that those are the sorts of simplest heuristics that one can implement in a sort of convolutional neural network to solve that task. And so in that sense, to the extent that we believe that convolutional neural networks are in fact implement these sorts of structurally simple algorithms, and we believe that in this particular task, the sort of structurally simplest way to do it is just these sorts of human-like image classification heuristics, then we think we're in fact going to be learning an algorithm which satisfies this training goal. Yeah.
You say that we believe that the simplest parameterization will implement human-like cat detection heuristics. Is that because of the implication of just simplicity in general, or is that because we preserve these things similar to our Windows on wheels examples from a few talks before?
Yes, that's a really good question. So I think there's a couple of things. So the first thing is, in fact, we could sort of think about this as like a pre-theoretic. If we didn't actually know what happens when you try to train a cat-dog classifier, what would the sort of arguments would, what sort of arguments would we have for why it would turn out one way or the other? But then you could also be like, okay, but we have built this thing, right? We've in fact trained, across the world, the number of times that somebody has trained a cat-dog classifier is very large. There's a lot of these that have been trained, and we in fact observe that, especially when we do transparency and we look at them, they really don't seem to be doing anything other than these sorts of basic image classification heuristics. Stuff like windows on top of wheels. And so we're like, OK, we have that sort of piece of evidence as well. One thing that we're talking about this more, sort of these various different types of pieces of evidence. One is sort of really important difference between the sort of, well, we looked at it after the fact type of evidence, and the, well, we have some reason to believe a priori type of evidence. Is eventually we're going to have to deal with situations where we have to determine whether these sorts of, we buy these stories and whether we think they're actually correct in situations where we don't know how they turn out, right? So if we were didn't actually know what was going to happen, when we trained a cat-dog classifier and we were just looking at this sort of basic story, we'd have to be, make some determination about how confident we really felt in it. And in this case, obviously it ends up being fine. But I think it's worth pointing out that the theoretical arguments, that we can make for, how likely it is for this to actually turn out fine, sort of a priori, are a little bit sketchy. I think that most of our confidence right now does really come from the fact that, well, we've done it a bunch, and we looked at it, and it doesn't look like it's doing the sort of, the bad thing. But it's, very difficult to sort of tell really strong stories about why we would have known that in advance. What sorts of properties, what sort of things could in fact have told us, in advance that the model would be doing the sort of, structurally simple heuristics that we want it to be doing. Yeah, question.
I mean, in the last talk, we went through the way it can develop deception, and it was that it already develops a good word model when it understands that it needs to take instrument systems and understands the situation well enough that it understands that if it pretends to do well, then later it can take over the world. I think we can a priori suspect that if we just gave it all the training data of cats and dogs and only pictures of cats and dogs and no text and no internet, anything, then it will be really unlikely to figure out its situation and in instrumental planning and so on.
Yeah, so I think this is basically exactly where we're going. So, the thing that you just described, is the sort of training story that we want, right? It is a, concrete reason to believe that there is a particular thing that would have to be present to, get some particular failure mode, and we think that that thing is not present in our training process, and therefore we think it's not going to yield, some particular thing, as instead going to yield the training goal that we want. Now, we want to be a little bit more strict than that, right? We don't want this, this is not just it won't produce deception. We also want it to be, well, it is going to produce the thing that we do want, right? And so we also need to have some argument for why, in this case, it's actually going to produce the sort of classifier that we want. But yeah, I think basically the thing that you're saying is correct. That's the sort of evidence that we're looking for, right? These sorts of pieces of evidence that can be really strong, strongly convince us that we're going to get a model that has these sorts of particular properties, and is not deceptive, because we have some good reason to think that. Okay, so these are the sorts of stories that we want to be telling. Okay, so some sort of facts about these training stories that I think are important. So the first thing that's worth pointing out is that these sorts of stories should be sufficient for safety. So if the model sort of conforms to the training goal, then it should be safe. So in this case, we have some argument as part of the training story as to why the training goal is safe. In this case, we think that human-like cat detection heuristics are safe because they're just the same sort of heuristics that humans use. We know that they're in fact safe. They don't yield anything bad. It would be really hard, for them to be implementing some sort of dangerous optimization procedure. We believe that a lot of the sorts of really dangerous things that models produce require them to be implementing some sort of optimization procedure. Given that we think that it's not going to be doing that, or given that we have a training goal, we say it's not going to be doing that. Given that it actually satisfies the training goal and is in fact not doing that, it should be safe. And then, if the training rationale holds, then we believe that in fact the resulting model will conform to the training goal, and so we have a reason to believe that we're actually going to get an algorithm, and that algorithm is in fact going to be a safe one. Okay, so in this case, again, the reason that we're sort of giving is we're like, well, okay, if the simplest parameterization that classifies cats from dogs, uses these sorts of human-like heuristics, then and we believe that gradient descent finds these sorts of simple parameterizations, then we think we should conform to the training goal. Okay, and these sorts of training stories are falsifiable. So I think one thing that's maybe worth pointing out is the training story I was just giving is not clearly true. So it's actually not clearly the case that actually we do learn only these sorts of human-like heuristics when we do cat-dog classification. I think there's some evidence that, and this is from adversarial examples, are features not bugs, where there's some evidence that actually sometimes we learn sorts of these sorts of features that are not human-like at all. They are these sorts of pixel-level features that are real features in the data. They do really correspond to things that are related to whether an image is a cat or a dog. But they're not the same sorts of high-level structural features that humans often use when they're distinguishing various different shapes. And so in that context, we can sort of believe that, well, we have this sort of very basic story. We might hope that even in the case of something very basic and structurally simple as cat-dog classification, we can tell a really precise story where we're just like, okay, we're going to get exactly this type of algorithm. We have these reasons to believe that this training process is going to produce it. But even then, it's very tricky because there are a lot of a bunch of subtleties to what sort of algorithm we might be learning, what sort of features might be paying attention to. And in this case, we're not super concerned about it. We have some understanding of what these sorts of pixel-level-like features are, and we don't think that they're doing some sort of crazy optimization that is existentially dangerous. But it is still worth pointing out that they're doing a type of algorithm which is not the sort of algorithm that we maybe wanted when we originally were like, okay, we think CNNs are maybe similar to how human image regions of human brain work, and so we're going to try to train something similar to human image classification. In fact, we often don't get that. We still get an algorithm that actually does do a really good job at the task, but it's one that is maybe a little bit different than the algorithm we were hoping to get. And it's hard, in advance to really be able to predict what sort of algorithm we're going to get. It's very difficult to understand, are we going to get these sorts of, weird pixel-level features? Are we going to get the sort of human-like features? In this case, we do get a combination of the two. But making these sorts of, predictions, getting the evidence required to be able to know, are we going to end up with this algorithm or that algorithm, is the sort of whole name of the game here. Yeah, question.
Are these training stories a standard method used in AI research? And if not, why not?
I don't think you'll hear many people using these same sorts of terminology. I really like them. I think we'll talk a little bit later about some of the sorts of other terminology that is often more common. Oftentimes, you'll hear inner and outer alignment used to describe some of the same sorts of things we're going to be talking about later. We of course talked about inner and outer alignment previously in a slightly different context. And I'll explain a little bit later on, what they sort of look like in this more general context. But I think that these are useful terms. I think that if you're trying to understand, how to think about, how to structure your own thoughts in terms of, if you're given some system, is this machine learning process going to be safe? I think this is the right way to think about it, regardless of what terminology you use. The right way to think about it is, have some understanding of what algorithm you think is going to produce and why, what reasons we have to believe, what pieces of evidence we have to believe that it's going to go there. OK. And then, again, I sort of want to point out that I think these training stories also are very general, right? So we can use them for cat classification, but as we'll see later, we can also use them for very complex alignment proposals. Any situation really where you want to rely on some AI system and that system was trained via machine learning process, you have to have some reason to believe that among the space of all possible algorithms that machine learning process could learn, why did you learn the one that you were actually trying to get? OK. So this sort of idea is anytime you're training a machine learning system, you sort of theoretically can have a training story in the back of your mind. When I'm training this thing, I'm training on this task, what am I trying to get? What sort of algorithm do I want it to be implementing? And why do I at all believe that among all the possible algorithms I could find, that's the one that I'm going to get? OK. So breaking things down a little bit more. So we've sort of been glossing over this, but within each class of the training goal and the training rationale, there's a couple of things that you sort of always need to have. So in the training goal, we always want to have a specification. We want to know, exactly what it is, mechanistically, the sort of algorithm that we want, and we sort of need this desirability. We also need to have some reason to believe that whatever that mechanistic algorithm is, we actually would like it. It's actually going to do good things if we got a thing that actually satisfies our training goal. So these are sort of both necessary. And then for the rationale, we sort of again have two things. We have these sorts of constraints. We have things that we know are true, sort of hard facts about the structure of our training process. And then we have sort of what I'm going to call nudges, which are the various different sort of individual slight bits of evidence that push us in one direction or the other. So the basic constraints are we know that it is in fact going to be some algorithm that fits the training data, right? This is the basic constraint of the structure of the training process. But then we also have a bunch of sort of things that are not those sort of hard constraints. Things that give us some piece of evidence in one direction or the other. OK, we think maybe this algorithm is slightly simpler than this other algorithm, but it's not sort of hard evidence. And so we're sort of going to try to isolate these things together. So we're sort of thinking about what are the sort of classes of models that we could find, and within those classes of models, why do we believe we might sort of be pushed in one direction or the other? OK. All right. I think one sort of important sort of thing to sort of touch on is how mechanistic do we really sort of need these descriptions to be? I think this is a really tricky question, and sort of a lot of the complexity of what I'm talking about right now comes in this question of when we're thinking about specifying a particular training goal, when we're thinking about specifying what algorithm is it that I want my model to be implementing, how specific do we need to be? And I think that one thing that's sort of worth pointing out there is that so if you sort of don't want to, if you specify too little, then you're in a situation where you're not actually constraining from a safety perspective, right? If I just specify, as we talked about at the very beginning, if the only thing I say is, well, I want some model that in fact does a good job on cat-dog classification, that's not enough facts, in theory, to know that your model is actually aligned. You need to know something about its generalization behavior, something about what it's actually doing, right? It is in fact doing something that mechanistically uses the sorts of heuristics that we want, is sort of specific enough in that case to sort of imply safety. But you need something that's specific enough to imply safety. But at the same time, if you specify too much, there's sort of this question of, well, why are we even doing machine learning in the first place if we already know what algorithm we want the model to implement, right? So if I know exactly what algorithm I want, I know exactly how it's going to work, I know what the structure is, well, I can just write that algorithm, right? The reason that we do machine learning at all is because we believe that, well, we don't know how to write the algorithm, but we know how to search for the algorithm, right? We believe that we understand a space of possible algorithms, and in that space, we think that there are desirable algorithms. And we have some reason to believe we can distinguish between the desirable and undesirable algorithms and find one that can implement the right thing, even if we don't ourselves know how to write that algorithm directly. And so, if we want to continue doing machine learning at all, we can't throw away, that basic thing that is the reason we do machine learning, which is, well, we don't know how to do what the algorithm that we want is. And so we need to have some description that is on a high enough level that it actually still allows us to do machine learning at all. And so this is sort of this sort of tricky, sort of dichotomy that we have to deal with between, we want to be as specific as possible because we want to sort of have some understanding that is clear enough that it precludes things that would be unsafe. But if we're too specific, then we've gotten into a situation where we've sort of eroded the advantages of doing machine learning at all. OK, so we want sort of as much specificity as possible while still being able to not have to describe exactly the algorithm and sort of stay competitive with other approaches. OK, so how much specificity is enough? So here's like an example, I think, of what sort of specificity I think that we really want in a training goal. So here's an example is corrigibility, right? So corrigibility, what is a sort of corrigible system? Well, the corrigible system here, Paul has a bunch of examples of the things that a corrigible system would do behaviorally, right? We're like, figure out whether I built the right AI and correct any mistakes I made. Remain informed about the AI's behavior and avoid unpleasant surprises. And a bunch of these, basic, facts about what we want the behavior to be. I think this is insufficient. So why do I think this is insufficient? Well, what's sort of happening here is it's sort of very similar to the thing we were talking about at the beginning, where we just described the behavior that we want from the model, but we haven't given any information about what mechanistically the algorithm it is that it might be implementing. And so I think this is sort of a problem, because it puts us in a situation where if this is the sort of basic target that we have, it's very difficult to understand, what would it actually look like to find an algorithm which has these properties? What sort of algorithms do have these properties, right? I think that this is sort of useful as a list of desiderata in terms of what properties we want. And to be clear, it's not the case that Paul is sort of intending this to be a training, goal here. But I think this is useful as a list of desiderata, but it's not sufficient as a training goal, because it doesn't tell us, given that we know a model does some of these things in the training set, do we have any reason to actually believe it's going to do the right thing later? So we need something a little bit more specific than this. So here's maybe a better example, and this is also from Paul. So here, Paul has a more specific case of what sort of model he's looking for. Yeah, question.
I'm a little confused about your example regarding corrigibility, because it says here that training goals need specification and desirability. So what algorithm we want and why we want it. Whereas the training rationale gives the constraints and the nudges. It seems to me that Paul's description of corrigibility is a training goal, but not a training rationale. So what exactly is it that it's missing from the training goal side of things?
Yeah, so I think that you could sort of use, it could be useful as a way to sort of have training goal desirability, right? It's a reason that you might like a training goal is that training goal is corrigible. But I don't think it is a training goal itself, because it doesn't give us a mechanistic description of what the model is doing, right? If you say, the model's corrigible, that's a property of the model's behavior, right? It is this thing that is saying, this model will listen to us and, change based on the things that we say, right? It'll try to correct, mistakes. That's a property of how the model acts, but it's not a property of what the model's doing, right? Like, what is it the model might be doing that causes it to have that behavior? So maybe a more specific thing, right, that you might have would be, we talked previously about this idea of corrigible alignment, the Martin Luther models, right? So you could have some description that's like, I want a Martin Luther model, and then the reason I think a Martin Luther model is going to be good is because I think it's going to have these behavioral properties of corrigibility, right? But you need that additional step. You need that reason, you need that sort of claim about what algorithm is it actually implementing, right? If the only thing that you have is, it is, I'm going to get a model that behaviorally is trying to act corrigible. As we sort of talked about a bunch last time, that behavioral analysis is just insufficient to be able to know whether the model is safe, right? We really need to have some additional facts about what it's doing internally to know anything about its generalization. Because in theory, if the only things I know are, it looks like it's doing X, it could be pseudo-aligned, it could be, deceptively aligned. There's all these sorts of various different things that the model could be doing that are consistent with any sort of behavior. And so we want to really be able to, in this case, have reasons to believe that among that set of models that are consistent with the behavior, why are we getting, what sort of particular one do we want, right? And so this is why I think the sort of basic, we want a corrigible model is insufficient here. We really want something more specific than that. So here's an example of something that's more specific. So here, Paul's describing this sort of, we want a model that has some model of the world and some way to translate between that model of the world and natural language. And so it does this sort of direct translation between the model's world model and the questions that we ask it. I think this is substantially more specific and sort of much more direct about describing internally what we want the model to be doing. It is saying we want it to have some model of the world that just sort of is sort of a plain model of the world, just describes how the model works, and then some way that directly and truthfully translates between the sort of concepts in the model's model of the world and the sort of questions that we ask it. That sort of direct translator is I think, a very nice mechanistic description of what we might want, right? We're like, OK, if we have a model, and the sort of algorithm it's implementing is it has some model of the world, and then directly translates facts from the model of the world into natural language, and it tells us those facts, then we have some reason to believe that, this isn't just an algorithm that looks like it's doing the right thing. It is really structurally doing the right thing. It is actually, in fact, honestly reporting its true beliefs about the world. And so now we have a reason to believe that it's doing the right thing. Now, importantly, this is still sort of a very high-level description, right? It's not the case that it specifies exactly how you would learn a world model and all of the facts that would be involved in that world model, right? We don't know all of those. We can't write them down. We're doing machine learning to try to learn them. but we still want to get a model that actually has this basic structural property that it does in fact have some model of the world that it truthfully translates into its outputs, right? And so we're like, if we believe we have that mechanistic property, then we sort of think we can be safe. And so this is the sort of level of specificity that I think we need at the very sort of at a minimum, right? Because if we have this level of specificity about what sort of algorithm it is that we're looking for, then we can start to reason about why we think that among all the possible algorithms, this is actually going to be doing something safe. Okay, so this is sort of what I'm imagining, right? We don't want something that is just this high-level behavioral gloss like corrigibility. We want something that is a little bit more specific in terms of describing mechanistically what it's doing, but not so specific that we're describing exactly all of the knowledge that it has. Okay. Okay. So that's the sort of basic high level, how to think about these sorts of training stories. And now we're going to sort of try to get a little bit into the nitty gritty, in terms of applying these and thinking about concretely what some, proposals for, how to build safe advanced AI might look like and how to evaluate them sort of in this framework. Okay. So I want to sort of go back to something I was saying earlier, which is, well, okay, what is sort of other terminology that you'll hear in this context? Previously, we introduced this sort of inner and outer alignment dichotomy. And we talked about them previously in these sort of strict contexts. So we said, a system is outer aligned if it, has, some loss function where if the model were optimizing for that loss function, we would be happy. And a system is sort of inner aligned if it has some mace objective, and that mace objective is sort of aligned with, it's the same as the sort of loss function we're trying to get it to optimize. And I think that in this context, these definitions are a little bit too strict. We sort of want to relax them. So what's sort of the problem with these definitions? And we can sort of think about them in a training stories context. So the sort of strict version of outer alignment and the strict version of inner alignment are both presupposing a particular training goal. They're saying, suppose that your training goal was you want a Mesa optimizer, you want some model which is implementing an optimization procedure, and you want that model to specifically be optimizing for the sort of thing that you specified in your loss function, in your, reward function, whatever, the thing that you specified that you were trying to get it to do when you were training. If that is your training goal, right? If the thing you want to get is a model which is actually doing, optimization, and it's doing it for this thing that you wrote down, then these sorts of concepts are exactly correct. They're the things that you want. They are, do we believe, the training goal desirability? Do we believe that if a model were actually optimizing for that thing that I wrote down, it would be good? And then the, training goal, the training rationale. Do I actually believe that I'm going to get a Mesa optimizer that actually has that goal, among the possible algorithms that I could find? But the thing that is worth pointing out is that, well, this is not the only training goal that we can have, right? So we might not want to build a model which is directly optimizing for the, some particular objective. We also might want to build a model that is optimizing for some particular thing, but the thing that it's optimizing for is different than the thing that we wrote down. It's not optimizing for our loss function, it's optimizing for something else. So, an example of this might be, I want to train a model that sort of acts in a similar way to humans. And the way that I'm going to do that is I'm going to reward it for, cooperating in some environment with other agents. And we're like, OK, well, we don't directly want a model that optimizes for cooperation, but we believe that the sorts of models which do a good job in this sort of cooperation environment have good properties, right? They're the sorts of models that, generally learn things like, be, cooperative, work with other agents, be nice, whatever. That's a training story that sort of is trying to train a model which is doing something different than the direct thing that we are trying to get to do, right? We have some loss function, we're directly training on cooperation. But we're trying to get a model that isn't just like optimizing for cooperation. We're trying to get a model that's doing something different. And so in that context, you can imagine if that sort of approach succeeded, then you would have a model that is aligned in the sense that, OK, it is doing something good, right? It's doing, it's nice, it's trying to cooperate with other agents, it's doing things in a good way. But it wouldn't be strictly outer aligned or inner aligned, because it would not be the case that if it were just optimizing for this raw cooperation objective, we would be happy with it. And it's also not the case that it is, in fact, directly optimizing for that strict cooperation objective, right? It's, in fact, doing something different than what we sort of directly specified in the loss function, but it's doing something different in a way that we want. It's doing the sort of correct thing instead. OK, so we need slightly broader terms, right? We need to say, in the more general case, where we have any possible approach that somebody might have for thinking about how to build a sort of safe system, we need a way of thinking about it that is a little bit more general than just assuming that the training goal is a model which optimizes for loss. OK, so what are the more general concepts? How do we sort of use this in a more general case? So here is our sort of training stories-based evaluation framework. So we have this sort of general notion of outer alignment. which is whether the training goal is good for the world, right? If we got a model and it satisfied the training goal, would we be happy with it, right? This is our training goal desirability. And in this context, we can sort of think about this as a more generalized version of outer alignment. It isn't saying, OK, the specific training goal of optimize for the loss function is that good. We're saying, OK, that might not be your training goal. Whatever your training goal is, you need to have some reason that if you actually got a model that had that property, you would be happy with it. And then we need a sort of notion of competitiveness. So we need to believe that if we actually did get that training goal, it'd be powerful enough to compete with other AI systems. So in this case, and this is sort of where it gets a little bit different from the more general training stories framework. In this case, we're thinking about powerful advanced AI systems, right? These are how we evaluate proposals for building systems that are arbitrarily powerful, for aligning the most powerful AI systems, for making sure they are sort of good for the world overall. And if your proposal is something like well, just do cat-dog classification, right? Well, that shouldn't be OK, right? That doesn't actually solve the problem. The problem was people actually want to do things that are not just cat-dog classification. They want to do all sorts of other tasks, and they want to use machine learning for them. And so we as safety researchers, right, need to find some way to figure out how to let the people do those things in a safe way. And so that means, just do cat-dog classification isn't an answer, right? We need to have some reason to believe that whatever approach we have here would actually be able to accomplish the various tasks that people want to use their machine learning system for. OK, so this is this performance competitiveness question. And then, again, we sort of have these training rationale components. So we have this sort of more generalized version of inner alignment, where we're saying, is it in fact the case that your training rationale is correct, right? Is it actually going to hold? I have some reason to believe, some piece of evidence to believe that I'm going to get this particular type of algorithm. Is that true, right? Do we actually believe that I'm going to get that algorithm among all the possible algorithms that I could find, right? And again, the sort of same reason that we talked about previously about why this might not happen, all the reasons you might get a pseudo-aligned model, a deceptively aligned model, these are reasons that your sort of training rationale might not hold. You might get a different model than the one you intend. And then we also need another sort of competitiveness portion here. So we need a sort of implementation competitiveness. We need some reason to believe that your training rationale, the sort of way you're trying to build your model, is actually implementable, right? So in the same way as train a cat-dog classifier isn't a solution, another thing that is also not a solution is just build a simulation of billions of humans. You're like, OK, if we just have enough humans and we simulate them in perfect fidelity and we get them to think about the problem enough, then they can solve it. And we're like, OK, that may be true, but we can't build that, right? We have no ability to actually, in fact, upload billions of humans and get them to think about the problem or whatever. And so we're like, OK, this is also not a solution. If we want something which actually sort of addresses the general problem of AI existential risk, we need some reason to believe that not only would it be able to sort of solve the problems that people want machine learning for, it also needs to be able to practically do so, right? It needs not just in theory be capable of doing it. It needs to also in practice be something we could actually do. OK, so we need these sorts of basic components, right? We need these inner and outer alignment, in the generalized forms, reason to believe that the thing we're trying to get is good and that we're actually going to get it. And then a reason to believe that we can do so in a competitive way, that it'll actually be able to solve the problems people want AI for, and that we'll actually be able to do so in a practical way. OK. All right. So we're going to now look at a case study, a particular actual proposal for addressing the general problem of AI existential risk. This is the first sort of concrete proposal we're going to look at in this series so far. We'll look at some more later, but this is going to be the one we have for this talk right now. And it's a particularly interesting example because it's one that is oftentimes very difficult to sort of analyze under a more conventional framework. So, but I think it's a really interesting proposal, and so I think it's a good place to start. So what is Microscope AI? So here's the approach. So the first thing that we do is we train some predictive model on some data. We want to get a model that is trying to sort of understand and sort of predict some particular distribution. And then we're going to try to use transparency tools to understand what that model learned about the data and extract that understanding directly and use it to guide human decision making. And so we're saying, OK, in the same way we can think about this sort of windows on top of wheels example. Well, we learned something about the model, what the model was doing. It was looking for windows on top of wheels. But if we didn't know things about cars beforehand, we also would have learned something about cars, right? We would have learned that cars have the property that they are detectable by looking for windows and wheels. Now, we happen to have already known that. But we might not have already known that, right? We have the ability to actually gain a ton of information and useful information that we can use for building our own systems and doing things directly that don't have to go through machine learning by using machine learning, right? The thing that machine learning does is it produces a model which has really good understanding of some data. We could maybe directly extract that understanding and use it ourselves. Yeah, question.
How do we actually know that these things will be inspectable by us, since the
Windows and the wheels thing is somewhat easy to detect, but if it uses some alien concepts with which you can 100% detect what a car is, how do we know that there is this sort of information to be gained? And also, perhaps give it that.
Yes, this is a really great question, and we're gonna talk about this very soon. I think the answer is basically we don't. We absolutely do not know that. And so, if you're trying to ask, is this, a actual solution? Which of these sorts of criteria does it succeed on? I think the answer is, well, it definitely doesn't. We definitely don't have a good reason to believe that it satisfies these criteria that we just talked about, right? It's not a solution, right? It may eventually become a solution, but we can. The thing that we're hoping to sort of understand by analyzing in this way is what are the things that we would need to have to believe that it is a solution, right? To believe that it actually does help with this problem, that this is an approach that we could use, to solve the sorts of problems that people want AI to solve, to do so in a way where we actually believe we're going to get the sort of model that we want. What are the sorts of things we would need to know to believe that, right? And so that's sort of what we want to understand here. Does it actually succeed? I think the answer is, well, we have no reason to believe really that it would right now, but maybe we could eventually get there if we have, really good transparency, for example, right? Some ability to actually believe we could extract, the sorts of concepts in a human relevant way. Then maybe, this would become a viable approach. I think that right now it's not a viable approach, but I think it's a really useful and instructive approach because it's going to help us understand how to think about these sorts of approaches in general, right? Yeah, another question.
How would this score under competitiveness? Like, let's say that we do have transparency tools and we can use those to understand heuristics the model have learned. Isn't that still significantly less effective than just running the model and letting it tell us things?
Yes, I'm really liking these questions because they're exactly the sort of thing I'm trying to get you to do, right? Which is take an approach and then try to analyze it, under these questions that we've been asking, right? Do they actually have these sorts of competitiveness properties that we want? Do they actually have these alignment properties that we want? I don't know. I don't know the answer to that question. I think that in this case, like I was saying, at least, it seems like there are at least some difficulties. And like you were saying, it seems it might be hard to actually get a system which can do all the sorts of things that we want. I'm going to talk in a little bit about going through those difficulties. But yes, I think that the thing you're saying is exactly correct, which is that there are competitiveness difficulties here that seem quite difficult. We'll talk about what they might look like. But yeah, absolutely. Yeah, question.
For example, now in chess and Go, these AIs very much beat us, and still Go players did improve, like after seeing, even without good interpretability, after seeing AlphaGo's moves, they did develop new strategies, and they develop, but still they are very far behind of the actual AI. Do you find it plausible that with good interpretability, we could understand the strategies of the AI so bad that human players could just learn that and beat the AI?
So I think that chess and Go is a particularly interesting example. So I think one thing I will say is that, well, OK, we don't just have to do it exclusively with human brains. We can still implement it in our own algorithms, right? So if you look at something like Stockfish, which is a human engine that uses substantially less AI than AlphaGo, or sorry, in like chess, for example, uses substantially less computation than AlphaZero. I believe that like current versions of Stockfish are better than AlphaZero was at the time when AlphaZero beat Stockfish. And that has done, that's partially through AI, but it's also a lot through understanding some of the things that AlphaZero was doing and trying to, actually write them in algorithms ourselves. So there is some extent to which, yes, I think the thing you're saying is correct. It does seem like there's a large extent to which, it's going to be really hard to get humans to the level of like these sorts of systems, but also they do teach us things, right? They have improved human performance, and they've also improved our ability to write other algorithms which do these sorts of things. So could this approach eventually succeed? I think maybe, but I agree that there's sort of some pretty major obstacles along these lines. Okay, so just talking about this a little bit more, Chris Olah, who's the head of interpretability at Anthropic, also is the person who created this approach. I think one good way of thinking about it is sort of what he talks about here. So the idea is that when you're doing interpretability, these sorts of visualizations are a bit like looking through a telescope. So just like a telescope transforms the sky into something we can see, the neural network transforms the data into a more accessible form. One learns about the telescope by observing how it magnifies the night sky, but the really remarkable thing is what one learns about the stars. And so the idea is, visualizing representations teaches us about neural networks, but it teaches us just as much potentially about the data itself. So the idea, this is the sort of basic idea behind this approach is, well, we are learning something about the network when we do interpretability, but maybe we're also learning something about what we were trying to understand. And so, we can sort of use better AI systems to improve, human decision making, and then, use that to sort of build better systems. Okay, so this is an idea. It's an approach that we can sort of think about as a way to, okay, we need some mechanism for being able to build systems which can solve these sorts of advanced tasks, and we need some mechanism for doing so in a way we believe it's going to be safe. And this is a mechanism, and so we sort of want to understand, is this a good one? Okay, so what's the training story here? So the sort of training goal, right, is a model that predicts the data given to it, and importantly, we want it to be sort of not optimizing something of the world. It's sort of just a world model, just doing some basic prediction task. And we want it to sort of be doing that in a way that's human understandable. We want it to be using concepts that once we understand and extract those concepts, we'll be able to understand what they're doing. So we want it to be sort of just understanding the world and doing so using human understandable concepts. And the reason we think we're going to get this, well, we think that if you just train on a prediction task on some really, really large prediction set, set of data, you're going to learn a just a pure predictor that's doing just prediction. Why do we think this? Well, one reason you might think this, it's unclear whether this is true, but one reason you might think this is, we were talking previously about this sort of, why would you get deception? And one of the things we sort of mentioned a lot was if the thing you're trying to train on, the actual objective you're trying to get to do is very, very simple, then the case for why you would get something like deception is much less, because internal alignment is actually really easy to describe. It's not like it takes this really long and difficult path, and so maybe it's more likely you would get that. So we're thinking, well, okay, if you're trying to train something that's just doing prediction, maybe we believe we're actually going to get something that really is just doing prediction. We have some reason to believe that, and so we think that we can get something that's doing the right thing. There's also separately this question of why we think we're using human understandable concepts, which is a really big and tricky question. I think maybe one way to think about this is, well, we'll talk about this in just a second, actually, in terms of why you might actually be getting human understandable concepts. I think that the most basic case is that you might get human understandable concepts for a while, and so you can use this as you sort of scaling up the power of your systems, but eventually you probably will stop getting human understandable concepts. Yeah, questions?
Even now with current image recognition models, it's not that clear that we do get human understandable concept. But I mean, sometimes we do, like these wheels and windows. This was a good example, but my impression is that sometimes we don't. And these are just very simple things working on some very under.
Yes, this is a really good point, because I made the exact same point earlier in the talk, right? When we were talking about the cat-dog classifier, it actually often doesn't learn just human understandable concepts. In just a second, I'm going to put up a graph that is sort of going to give a rationale for why you might expect this to work when that doesn't work. But I agree that it's a serious sort of concern and problem for this style of approach. Okay, but yeah, so let's talk about why you might expect this to work. So in terms of the training goal, we need this outer alignment. So whether the training goal is actually good for the world, right? So is a pure predictor actually safe? If you have this pure predictor, is it actually going to be okay? Are you going to be happy with it? And this has a bunch of different questions. So one is like, are we actually going to be able to make use of it, right? Is the knowledge, actually, the sorts of knowledge which helps humans, which makes humans actually like, do good things, or does it make them do bad things? We also have sort of tricky questions about whether predictors themselves are safe. And this is something we're going to be returning to in a later talk, but we have things like self-fulfilling prophecies. So if I have a predictor and that predictor is trying to produce predictions such that those predictions are very likely to come true, then I can have some system that is like, well, if it says the stock market goes up, then people trade on it and the stock market goes up. And if it says the stock market goes down, then people trade on that and the stock market goes down. And so any prediction the system makes might be true. And so we might be a little bit concerned that it's actually going to produce the sort of prediction that we want, because any of them are equally valid. This sort of thing can get a little bit tricky. Again, like I said, we're gonna come back to these sorts of difficulties dealing with predictors later. But suffice to say, there are some sort of issues that you might be concerned about, even if your model is just doing a prediction task. Okay, And then again, we talked a bunch about this, but we have this performance competitiveness issue, right? Is it actually sufficient to accomplish all the tasks you might want with the AIs just to be able to do this, information extraction in terms of, extracting the knowledge that the model has learned? The answer is maybe. I think that my best guess would be it is possible for some tasks and not for others. So especially for tasks that involve, a really large deployment or a really, fast response interval. So something like a dialogue agent or like a, factory agent. A lot of things where you need an AI to be doing something directly in the world and be doing it in a lot of different cases. It seems very difficult to make something, using this approach. But there might be other situations where you might theoretically have otherwise wanted an AI system that this can sort of cover for. So maybe you wanted to build AI systems to, as managers in a company. Maybe this sort of can give you an alternative to that, which is, well, maybe it's actually better to sort of use the AI system as a way to extract really useful information about how to do management and then give it to humans. And so it's certainly a situation where you could imagine a lot of possible use cases sort of being solved by this. But I think my sense would be it does seem like there's some use cases where you're going to really want AI systems that this sort of doesn't address. And so you're like, well, if this is our only proposal for being able to sort of make safe systems, then you might be very concerned that there's still going to be a bunch of possible ways that you can build AIs that this sort of doesn't address. OK. And then, so for the training rationale, we have this sort of inner alignment question. Is this sort of training rationale likely to hold? Are we actually likely to get sort of human understandable concepts by default? Are we actually likely to get a predictor? So I talked about the sort of are we likely to get a predictor question. This sort of riding on the simplicity of the prediction objective. I promised a graph about how likely it is that you would get human understandable concepts. So here's that graph. So the idea is this is sort of a hypothesis. It's unclear whether this is true. But the idea would be, well, maybe as we sort of increase the strength of our models, the way in which we get the sort of concepts that those models learn change like this. We think that as we have really simple models, maybe they're really hard to understand because they're doing something as we have really simple models, they're very easy to understand. We have something like linear regression is very easy. You just look at the the weights. It's got a slope and an intercept. And then we have slightly more complex models, and they get substantially more confusing because they learn these really weird concepts. But then you get more powerful models, and then they start to learn these really simple abstractions, these really basic, structurally simple concepts, the sorts of concepts humans use. But then, as you keep pushing further, you get weirder concepts that are like better than the ones that humans use, and ones that maybe we don't exactly understand. And so it starts to get worse. This is a hypothesis. I think that we have maybe some data to support this. We have looked at how hard is it to interpret models over time. I think that we have seen this to some extent. So there are things where very, very simple models are very easy to interpret. And then you have more complex early vision models, stuff like AlexNet, that are often very hard to interpret. And then with later vision models, they often get easier. So especially once they have stuff like residual connections, they start to become use concepts that are easier to understand. So there's maybe some evidence to believe this, but we have no reason to believe that we would get necessarily this exact sort of shape around here. So maybe this would work, but it's unclear. But this would be the sort of thing that you'd be relying on if you were sort of, is this going to work? We actually think we're going to sort of rely on this proposal. We need to sort of be able to rely on something like this graph holding. OK, yeah, question.
I may have missed this, but has this been observed to happen up to like a certain point already? Like, have we started to see this curve go down and then up again?
Yeah, so I mean, I think we have seen this at least with early vision models. So like really, really simple vision models, where it's just like doing, hard-coded edge detection, we understand it. Early CNNs are very hard to understand, but later CNNs are often easier. At least with simple vision models, I think we do see this sort of this U here. But even that is a little bit subjective. It's just based on, well, people have looked at these and how easy is it generally to find concepts in them. But I think that we sort of see something like this U happening for simple vision models, though it's very unclear. Yeah, question.
This diagram looks pretty similar to deep double descent for lecture 1. So is there any connection to that?
I don't think so. I think that, I think that it's not doing that. I would say that in some sense, this is sort of the inverted of what the double descent graph looks like, because like with the double descent graph, the idea is that performance sort of goes down here and then goes up, whereas here we sort of, I guess if we're thinking about interpretability as performance. Though, of course, we're imagining that the reason it learns these alien abstractions is because they improve performance. They're better than the human abstractions. And so, yeah, I guess you could maybe think of like this point here, where it learns these really confused, difficult to understand abstractions as like the worst part of the double descent. You start with these sort of, relatively, you get simple things, then you go up and you get these sort of dumb memorized things, and then over time you get, simpler and simpler things. And some of those early simple things maybe are human-like, but then eventually you get these sort of simple things that are non-human-like. So if you wanted to sort of superimpose it, it would you would look, more like with the hump of the second descent there, probably. But I don't think that there's necessarily a clear relationship. But in terms of trying to analogize and understand. Yeah, another question.
So I'm not sure if this is straightforward to answer, but what's the force that's pushing the model to go towards increasing alien abstractions? If you're trying to predict data that's been generated by humans, and like humans have human abstractions, it seems like that's the useful level of abstraction to reason about predicting the data in, since that's how it was generated. So is there really a reason to push beyond that when, like, once you get there, you probably have like a good ability to start predicting that data?
Plausible. I think the thing you're saying is absolutely plausible. But I think there is an alternative case. The alternative case would be, well, a lot of the data is just the world, right? It is just like, how do things in fact function in the world? How does the world work? What sorts of things happen in it? And how do those things relate to each other? We as humans understand some of those things, right? We have the ability to understand and predict various things that happen in the world to some degree, but we're not like experts at it, right? There's all sorts of things about the world and concepts and relationships in the world that we don't fully understand, that we don't have great concepts for working with. And so you can imagine that, there's room for improvement, right? There's no reason to believe that just in terms of basic concepts for understanding what happens in the world, the humans are, at the absolute forefront. And so you could, imagine getting substantially better concepts than the ones the humans have, even in just the sorts of for understanding humans, right? If you're just thinking about good concepts for psychology, right, for understanding human behavior, there's no reason to believe that human concepts for understanding human behavior are at the limit, right? There could be better concepts for understanding how to think about, even how humans work, right? There's a whole field, of psychology, right, that tries to produce better concepts for understanding how humans work. There's no reason to believe that, we are at the limit of psychology or something. Yeah, question.
To go back to the chess example, we have a neural network, what says, would you think that the current systems are already in the increasingly alien abstraction domain, or would you say that we try interpretability on those, we would get crisp abstraction? What do you make of it?
Yeah, that's a really good question. I think the answer is maybe. There's some interpretability work that has been done on like AlphaGo, where some very good, chess and Go players have tried to look at some of the things that the model, is paying attention to and understand what it's doing. And sometimes we understand, and sometimes we don't. It often, there was some work that found that a DeepMind paper that found there was like a large amount of correlates between, the sorts of things the Stockfish pays attention to and the sorts of things that you can sort of probe out of AlphaZero. But even then, it's not perfect. There's a lot of things that it's clearly paying attention to that are different than the things that we know how to pay attention to. So it's unclear. I think the answer is, maybe. Okay. And then, yeah, so implementation competitiveness, how hard is this actually implement? There's some questions, how hard is it to actually build, a system which is doing, prediction? Hopefully this is not that hard, because this is like one of the most basic things that we often do in machine learning. But there's also a question, which is how hard is it to actually use the transparency tools? That might be extremely difficult, right? It may be the case that actually, even if we can extract the concepts, it's very computationally intensive or human labor intensive to actually be able to understand and interpret, in which case that could be another thing that's a real, a very serious problem here. Okay. So we have some understanding now of what it sort of looks like, to sort of understand this proposal. We have these ideas, how to think about, what the competitiveness is, how to think about, the alignment. Overall, I think that there's some reasons to like this approach and some reasons to not like it, right? Places where it might be helpful, places where it might not be helpful. The idea of doing this sort of analysis is to understand, when can we trust it? When can we believe that it's going to solve various problems that we have? So that we can figure out how to make use of these approaches, right? So that we're not just, here's an interesting approach. We have some understanding of how it actually fits in to, the broader picture of, how we can use various different approaches to sort of, eventually, as humanity, have ways to be able to address all the problems that we need to be able to address. Okay, so now sort of for the sort of the last bit of this talk, I want to sort of take a step back and talk a little bit more generally about, what are the various different sorts of training stories that we might tell in general? Where do we get evidence, right? What are the sorts of training goals we might imagine? And what sorts of pieces of evidence might we find, and ways in which we can have to generate evidence to believe that, some particular, training rationale would hold. OK, so what are some training goals? So, one example, of course, is the example that we talked about previously in this sort of strict inner-outer alignment sense, right? Which is, maybe the training goal we want is we want a model that is just directly optimizing for that, loss or reward function that we specified. We want a model that is just directly doing the thing that we wrote down. This is one thing we might want, right? It is absolutely a thing that you might be trying to get in various different circumstances, right? Now, it's not always the thing that we want, right? So in Microscope AI, it's definitely not the thing we want, right? We're not trying to get a model that is like minimizing its, its accuracy on something. We're just trying to get a model which understands the world, right? In some very, general sense. And so it's not always the thing that we want, but it sometimes is, right? Sometimes maybe that is the sort of goal that you're trying to get. You actually believe that you have written down an objective that captures everything that you care about, and you want a model that just is trying to optimize for that objective. So, the idea would be that, in this case, we sort of have a model that is, instead of optimizing for some direct thing, it's sort of just optimizing for the reward. Now, the problem with this training goal, right, is that it's sort of a little bit dangerous, right? Because we have a situation where, we sort of get reward hacking, potentially, which is this idea of, well, it's very, very difficult to have a reward function, right, or a loss function that actually fully specifies all the things that you care about. And so there may be situations where the model can sort of get something which satisfies the technicalities of the loss, but doesn't actually do the thing we were really intending it to do. Classic examples of this are situations where there's this sort of classic boat game where OpenAI is trying to get the model to get a boat to sort of go around in circles, and it discovers that it is actually trained on was sort of getting these gold coins in the race that are sort of spaced around, and it finds that it can just sort of run in circles, hitting up against the wall to get this one respawning coin over and over again. And so the idea is, well, this was technically a thing that satisfied the loss function, but it wasn't really the thing that we intended. And so this is sort of a thing that you can be really concerned about with this type of training goal. So we really want alternatives. OK, so here's another thing that we might want. Maybe we want an agent that is sort of myopic. So we talked about in the case of deception, one thing that we were really concerned about is agents that are sort of optimizing for things over a long time horizon, right? They care about something in the world. They want to get something in the world over the long term. And that's sort of the reason that they try to deceive us. So maybe the thing you want is you want an agent which isn't trying to optimize anything in the long term. It just has some sort of short-term goal. This is like another thing that you might want. This is another sort of type of training goal that you could have. But there are problems here too. So issues that sort of arise in trying to make these sorts of training goals desirable are related to these sorts of issues we were talking about self-fulfilling prophecies, and sort of issues we're going to talk about later about in case we have these agents that are just trying to optimize one thing in the next time step. There are cases where that can sort of break, where that's sort of a very brittle abstraction. So, a simple example might be if I am just optimizing for my one time step, but I know that I have the ability to sort of cooperate or not with a bunch of other agents that are also optimizing for their one time step, then we can all sort of agree, well, if we do this thing, then it'll be best for all of us overall. And so they can all sort of cooperate and coordinate on doing one individual thing that is best for all of them. And that can, in practice, look like optimizing over a very long time horizon because they're sort of coordinating together over time, even though each one individually only cares about one sort of time step. So you can have examples like this where it sort of gets very tricky. But this is another thing that you might desire, right? We want something which is really just optimizing over the short term. OK, another thing we might want is a sort of truthful question answer. So this is similar to the thing we were talking about at the beginning, right? Paul's example, where we have a model and it just sort of truthfully translates between its model of the world and the questions that we ask it. It's this sort of direct, truthful translator, honest question answer. There are various ways which we might try to get this. Things like debate and amplification, which we'll talk about later. But something which is just sort of directly trying to answer questions truthfully. OK. Maybe we just want, one thing we might want is we just want it to learn human values, right? It is totally, a possible training goal, is the sort of most fully ambitious training goal, right? We're just like, we want a thing that is just directly maximizing for, the things that humans care about, right? This is maybe, the most original, most basic thing that oftentimes people who've thought about AGI have sort of wanted. but it's only one of many possible things that we might be trying to get in various different circumstances. It is one thing that we might try to train a system for. It's worth pointing out it's probably the hardest thing of all of these, right? It's a really complex goal. It's one that's very difficult to specify, right? So it's one that can be very difficult to get. But it might be your goal, right? In some cases, eventually maybe, we might want to build these sorts of systems. Though I would say we probably don't want to build these sorts of systems in the short term, at least. OK, we talked about corrigibility, right? So I was saying corrigibility, in this sort of basic behavioral sense, is not, good enough as a adjective. But there might be other senses, right? So we talked about the corrigibly aligned models, right? Like the Martin Luthers. Might be another sort of thing that you might be trying to get. Yeah, question.
Sorry, I just realized that I don't really understand how loss minimizing models would fit into this list. Like, why would that be safe? Like, what would be the loss function for which it would be safe? Isn't it the fully aligned already?
Yeah, I mean, so I guess that there are some cases where it might not be the case that the loss function specifies everything about human values, but it still specifies enough that you're sort of OK that it's not going to like destroy the world, right? So maybe your loss function specifies something about impact regularization. So it specifies, I want you to, just fetch the coffee without doing anything else crazy in the world, right? And maybe if you actually believe you've really nailed down what it means to not do anything else crazy in the world, then a model that is really just optimizing for that would be OK, right? And so there are cases where you could have a loss function, right, and a model that was just directly optimizing for that, and you'd be OK with that, even though that loss function wouldn't imply that it's doing the right thing in all situations. It at least wouldn't be doing a sort of sufficiently wrong thing that you would be really concerned about that that would be bad for the world. OK. And so, right, so corrigibility. So, we don't want this sort of behavioral description, but maybe we could get something more mechanistic, like the sort of Martin Luther models, right? OK. We've talked about this sort of predictive models. Models like in the Microscope AI case, we were just trying to train a sort of predictive model that is just trying to do some, it's sort of trying to understand the world. It has some world model. It's just trying to do some prediction task. We're going to return to this specific case more later, because there's a lot sort of more to talk about in terms of what it might look like in this sort of specific case. And I think this is often what a lot of people want with large language models. And so this is sort of a pretty common training goal. And I think one that has a bunch of really interesting properties. It's another thing that you might want. People often refer to these as sort of generative models or simulators. The idea is, a model that really just has some world model, is trying to do a basic prediction task based on that. OK. An important thing to think about is the sort of difference between the predictive models and the truthful question answers. So the truthful question answer also has a world model, but it answers questions truthfully. So if you ask it, some question about the world, it will tell you exactly what is true about the world. Whereas the predictive model will only tell you, what you would observe, right? So the predictive model is maybe predicting, what would show up on the internet in some particular case. What is most likely, what sort of tokens are most likely to occur on the internet? What sort of tokens are most likely to occur in some particular situation? And that's not necessarily truthful. So the predictive model is not always truthful, whereas the truthful question answer is always truthful. Yeah, question.
So does that mean, like, theoretically, if you could train either one of those agents, you would always want to train the truthful question answer, and there's no advantage the predictive model has? Is it just that the predictive model is easier to train with our current method?
Yes, I think that's basically right. So if you could theoretically train either one, it would be equally easy. You would want to train the truthful thing. But maybe you think that it's too hard to train the truthful thing, but it's easier and sufficient to just train a thing which is making more general, just like predictions. OK. OK, so another possible thing is sort of narrow agents. So maybe you want an agent that's sort of related to the impact regularization thing that we were talking about previously, that just solves some particular narrow task, but doesn't do some very general optimize for human values in some very general case. It's just trying to get the coffee, and you're trying to train it in a case where it's not going to be doing any other things, right? This is like another sort of thing goal that you might want. Another training goal is this sort of concept. I think that exactly how this thing would work mechanistically, that was a little bit poorly understood, right? What actually would it look like for an agent to be doing something like this? There are some possible hypotheses. So something like quantization would be an option, where the idea is it has some objective, but then rather than optimizing for that objective, it only sort of takes the top 10% of outcomes and then uniformly randomly picks from among them. And so maybe that is a lot safer because it's not sort of directly optimizing. It's just sort of doing some narrow task and only so well. OK. And I definitely, one thing I really want to point out is that this is not an exhaustive list. So the idea of this sort of thinking about, AI in this way is not to sort of be like, OK, these are the possible options, pick one. The idea is to sort of really thinking about, OK, what are all of the different possible things that you could have a machine learning process try to find? What are the sort of algorithms we might want, so that we can have a large possible space of what are the things we might be trying to get. So we can think about which things do we want in different circumstances, which things are going to be safest, which things are going to be easiest to get, et cetera, et cetera. OK. OK, and so we might also want to do the same thing with rationales. So we've talked about this these are sort of possible goals that you might have. We also want to understand what are the possible ways of gathering evidence about these particular types of training goals. What things might convince us that you would actually have a machine learning process which would get a model which is well described in that way. So what might that be? So one thing is inductive bias analysis. So we've talked, this is sort of the thing that we spent a bunch of time doing in the previous lecture, really trying to understand, OK, in various different versions of the inductive biases of the machine learning system and how we can think about them, how likely is deceptive alignment, right? And this gives us some information, right? It tells us some things that we can predict about how likely is something like deceptive alignment in various circumstances. But it's a very difficult piece of information to work with because it's really uncertain. We don't know that much about the inductive biases right now. And so it can be hard to sort of really reason about this rigorously. There are some examples of sort of doing this a little bit more rigorously. So I have one over here that is a little bit more rigorous example of inductive bias analysis. But being a little bit more rigorous, it's also much more narrow. It's sort of focusing on a much sort of narrower task. But you can try to do this. You can try to sort of work through these things in theory and try to understand, based on various different versions of the inductive biases, how would things go. This is also using a much more sort of a very theoretical sort of notion of inductive biases that is not maybe very well-grounded. And so there's often here a lot of tension between inductive bias analysis that we can do in theory and actual practical inductive biases that would exist in practice. And so we saw a lot of this tension previously where in the last talk we had to use these entirely two different notions of inductive biases to even have any reason to believe that we're going to get some convergent result at the end. OK, so that's one way that we can do it. And one advantage of the inductive bias analysis, of course, is that it's something that we can do sort of in theory even before we built the system. Transparency interpretability is sort of the opposite. This is something that we can do sort of often. It can give us a lot of information. If we just look at the model and we see, it's doing windows on top of wheels, we can get a ton of information about what it's doing. But it's something that is sort of very difficult to do in advance, right? So we can maybe do some transparency interpretability on early models. We can maybe see how it's being trained to do transparency interpretability along the way, sort of see how it's developing. But this is, it's very difficult to get information about the model in advance by doing transparency, because we often have to sort of build the model and then figure out what it's doing. And that can oftentimes be sufficient. It can be OK to just build the model and then look at it and see if it's OK. But it also can be a little bit tricky if you sort of think that just building the model might itself be dangerous, which at least for sufficiently powerful models is potentially a possibility. But another thing I would say here is I also think this is maybe the strongest piece of evidence on this list, right? What is the thing that would most convince you that the model is definitely doing the thing that you wanted? Well, we looked at it, we understood exactly the internal structure, and it had this internal structure, right? It's doing exactly this thing. And so maybe, I think in some sense, this is maybe one of the strongest pieces of evidence if you can get it. Though it's very difficult to get because you have to actually do this transparency and understand the concepts that it's using, which can often be really tricky. OK. So another thing maybe is this sort of game theoretic analysis. So if you were trying to think about something like the train for cooperation, right, that we were talking about previously. Well, why would you believe that train for cooperation would work? Well, the training goal there, right, wouldn't be just directly optimized for cooperation. The idea would be, well, maybe the sort of equilibrium of various agents playing in this environment is the sort of equilibrium that we want. So and sort of example of this approach is sort of thinking about, well, maybe humans in fact learn some particular values, and we learn those values based on them being good in some ancestral environment. So you're like, okay, maybe we can have some environment where the equilibrium solution, the agents that you would be most likely to learn would be the sorts of agents that would have the sorts of values that we want. So you could try to get some evidence by this, doing some sort of theoretical analysis or empirical analysis of in some environment, what are the sorts of agents that are likely to do well in that environment. They're likely to sort of cooperate and coordinate with other agents that are likely to sort of survive, thrive, pass multiple rounds of natural selection, et cetera, or in this case, artificial selection. OK. Another thing that's maybe worth pointing out here is capability limitations. So you can have situations where the reason that you believe your model is going to be implementing some particular thing is just because you didn't give it a bunch of information, or you just didn't give it the ability to implement some other thing, right? So if you think about something like the cat-dog classification example, maybe the reason that you believe it's safe is just that, well, it's such a simple task that it can't possibly learn these really complex things that would be necessary for it to do something dangerous. So this is like another piece of evidence, important piece of evidence that you can use here. One example of this is trying to sort of maybe restrict modeling humans, because maybe you believe that being able to understand humans is really important for being able to deceive humans. And so maybe if you just don't try to give it understanding about humans, then you could be more confident in it. Of course, that's hard because we often want to be able to understand humans. So this can get very tricky, but it's another piece of evidence that you can use. OK, having oversight, right? So another way you can get evidence is, well, throughout the entire process of building the model, I've been able to look at it and understand what it's doing. We're going to talk later on about what these sorts of oversight processes might look like, amplification, debate. But the idea is, well, OK, if I have some way of sort of continuously overseeing the model's behavior, then that gives me some information to sort of predict, well, OK, I have some reason to believe that it's going to be doing the right thing because I've been looking at it as I've been training it. Another thing that I sort of like to talk about is the sort of AI cognitive science idea. So maybe just by looking at the model's behavior, we can build hypotheses about what sorts of mechanistic things it might be doing internally, and then put the model in various different situations to test those hypotheses, and then extrapolate forward. So if we're thinking about, OK, we have two different training regimes, we want to understand how likely is that training regime to yield a model that is optimizing something over the long term or not. We can build hypotheses about what would it look like, what sort of consequences would happen from a model that's doing that versus not doing that. And then we can figure out, OK, does this training procedure yield that sort of model or not? And then we can predict, OK, if we keep doing with this training procedure, it's likely to yield things which are consequentialist, and in this training procedure, it's not. And so we can sort of use that as a way to predict what sorts of behaviors are we going to get later on. One thing that's very tricky with this sort of approach is that it's very behavioral, right? We're just focusing on, OK, making inferences based on things that we observe about the model's behavior, which of course, can get us into problems with deception, like we were talking about previously, right? Where you can't always be fully confident that the model's not deceptive just by looking at its behavior, because it could be trying to trick you. OK, so one thing that's sort of very related is the sort of precursor checking, which is, well, instead of, if we think that behavioral checking is always sort of going to be potentially running into issues, well, maybe instead of looking for something like deceptive alignment directly, since if you look for deceptive alignment directly, then the model can always sort of be trying to trick you, you look for some precursors, things that are necessary for deceptive alignment to arise, but not deceptive alignment itself, right? So is the model, thinking about something, thinking about the training process? Is it optimizing a long-term goal, right? You're like, OK, what if we just look for those sort of precursors? Then maybe you can have more confidence, right? Even if only doing behavioral analysis. Another important sort of component of something like this, so yeah, another thing you could do would be like loss landscape analysis. So this is sort of related to the inductive bias analysis, but maybe sort of on the more high path dependent side. So with the inductive bias analysis, we were thinking about something more low path dependence, where we're just sort of thinking about simplicity and and speed. But you can also think about things directly by looking at the the basins, trying to understand how likely would various different paths through model space be. So it's worth pointing out that there's both low and high path dependence versions of this. And then finally, another thing is sort of, this is related to the precursor checking idea, is you could do sort of scaling laws, where you try to understand, as I vary various properties about my models, how does it change various alignment properties, right? And I can use that to sort of predict, as if I'm training in this particular way, I generally get models that have long-term goals, and I train in this way, I generally get models that don't, and I see the long-term goals going up here. Then you can predict that it's going to continue going up, and you're going to eventually end up potentially sort of in the regime where you can get something like deception. So you can use these sorts of ability to understand earlier models to give some information about what future models might do. OK. And again, this isn't an exhaustive list. There's lots and lots of other ways that you can get pieces of evidence and information about what sort of algorithm your model is going to be learning. But the basic idea is this is the sort of business we want to be in. We want to be trying to gather information this way to help us distinguish between possible algorithms that the model could be run. OK, and then one very final thing that I want to talk about is once you have this training story, you have some basic understanding of what mechanistic algorithm you want to be doing, why you believe it's going to be doing that. You also sort of want to then really have some ability to understand, OK, how robust is this understanding, right? We have some reason to believe that we think maybe this training process is going to go through, this training story is going to be correct. But then you also sort of really want to be able to put in a bunch of analysis and be able to get probabilities out, be able to understand, OK, do we actually trust this, right? Because there's a really big difference between, OK, this training story sort of makes sense. I maybe understand why it would go through, and like we're super confident, we're willing to stake the world on this being true. We have like very good rigorous analysis, right? And so we sort of want to be able to understand, OK, how can we get to that point, right? Like what are the sorts of things that you could do to really test and probe at your training story? So the idea is this sort of sensitivity analysis. So you can analyze how robust your training story is by looking at sort of how sensitive it is, right? So you can be We can look at other, similar smaller models, see how they fail, extrapolate those failures, right? If we have a bunch of other training stories, and we've seen how well those training stories do in general, we can have an understanding of how likely is any given training story to succeed, right? So we think about something like the cat-dog classification example. We can be like, okay, maybe a priori we expected it to do this particular thing. We expected it to do, human, concepts, and then we found out that it didn't, right? And so we're like, okay, in general, when we build training stories, how often do those training stories actually match on to what we find? And so, how often are we wrong, right? And so we can use that as some understanding of, okay, as we start building more and more complex training stories that are more and more difficult for us to really predict in advance, how often are we actually able to get them right? We can also just sort of characterize the space of possible models, right? So, we did this, previously. We were like, okay, some of the possible options you could get are things like, the Martin Luther models, the deceptively aligned models, the internal aligned models, all these different types of models, and that gives us some understanding of at least what the options are. So we can understand, okay, how bad would the possible failure modes be? Can we at least rule out, some of the worst possible failure modes? And we can also sort of look at even direct sort of perturbations. We can be like, okay, once we have training stories which are as mechanistic, really mechanistic and really clear, okay, we think we're going to get exactly these sorts of algorithms, we can start to understand, what happens if individual parts on that path go differently, right? So we were talking about, in the high path dependence case, where we're thinking about, this is like the path to the correlation line, the Martin Luther model. First you learn these sort of world modeling and proxy objectives simultaneously, but then and then you sort of eventually gets replaced with a pointer. But the deceptively aligned question, we can sort of ask, well, what if there was a small perturbation, right? What if instead you learned, first you learned, how to understand the training process and you use that, right? And so we can sort of think about these paths and think about, well, okay, what if, various individual things in our understanding of how the sort of model is going to, be trained were slightly different. And we can sort of, reason from these perturbations to maybe sort of start to have some more confidence that even if our model was slightly wrong, things would sort of still go the way we want. Okay, this is again not an exhaustive list, but the idea is, some ways to sort of, once we have these training stories, we don't want to just be done with like, okay, here's a maybe plausible case for why we think some machine learning training process would yield a particular algorithm. We really want to be as robust and as confident as possible that this training process is actually going to yield the algorithm that we want. Okay, so that's the end of the talk. Hopefully this was a little bit helpful for starting to get into understanding, evaluation, right? Starting to get into understanding, okay, we have some idea of the problems, how do we actually figure out how to evaluate various different proposals. Okay, any last questions? Yes.
You've said world models a couple times in this talk and the last talk. Could you tell us exactly what you mean by a world model?
Ooh, that's a tricky question. Yeah, I mean, I think that, and this is maybe something also I want to we'll sort of touch on a little bit when we talk about prediction, but it's tricky. I mean, I think that the basic idea is we're like, okay, it's some understanding of the world that is not necessarily sort of that is separate from how you act on that understanding, right? So you have some way of understanding facts about the world, patterns in the world, things that you know about how the world works. And that's distinct from, okay, given that I know these facts about the world, and I'm trying to achieve, goal X, I choose to output, action A, right? And so we have some understanding that is like, okay, we really want to separate those things. We want to separate your understanding from the way you use that understanding to produce outputs. And so we sort of want to call the understanding part the world model. Now, I think that that separation is a little bit fraught. It's not clear that it's always even possible. But oftentimes it is a really useful piece of analysis. And so we'd like to be able to do it. But it is, I think it is really tricky. Yeah. OK, well, we'll call it there. So yeah, hopefully that was good.